So hey everyone, as they said, my name is Mia Henderson. I'm a site reliability engineer at PagerDuty. A little over a year ago, we started our container journey at PagerDuty, and it's been a ride. We now have over 10 services running in containers in production, and we're in the midst of setting up a container scheduler. We've learned a lot, and I hope you can learn from some of the mistakes that we've made. My team's first foray into containers was a development environment based on LXC and using Chef. LXC at the time didn't have very good high-level plumbing, and we spent a lot of time in the piping things together, and it didn't really work very well. We quickly realized that we needed something that had easier, faster-to-learn tooling for our end users. We started experimenting with Docker, and we were quickly using it for development environments for a number of our internal projects. It was well documented, easy to learn, and it mostly worked. At the time, we had a very inconsistent set of deployment tools, mostly consisting of really old versions of Capistrano and really old versions of Capistrano recipes. We deployed dozens of times per day, and each of those deploys can bring down our whole infrastructure. So having a rickety deployment infrastructure is really a high risk and not great to have. So we decided we needed to standardize our deployment environment. And one of the ways that we could do that is by deploying containers rather than by deploying individual applications, which each have their own buttons and knobs to turn when they deploy. So we decided to give that a try. Our first Docker app was one of our existing services, and we converted it to run in Docker. We chose a simple service that was well instrumented and easy to test. It was a basic API on top of a data store written in Scala. We modified its Chef role to install Docker and used the existing configuration files dropped by Chef mounted into the container. We were trying to minimize the need to modify the application to run in Docker. Our goal was to improve deployment, not resource utilization. So we still used dedicated hosts for each container, trying to keep it simple and keep it more similar to our existing infrastructure. We weren't in it for resource management. So we also didn't apply any Docker-level resource management since the containers were on dedicated hosts. For logging, initially, we didn't actually modify the application to even log to standard out or standard error. We used Splunk as our centralized logging system. So we just mapped a drive into the Docker container and logged to there and had Splunk pick up those drives, pick up those logs and log rotate as well. So we use Datadog for metrics, but basically it's just a modified statsd collector. We wrote some IP tables rules so that any Docker application could write to an arbitrary IP address on port 8125, and the metrics would just get collected by the Datadog agent on the host. We could have run a Datadog sidecar container with our containers, and we tried this, but it seemed unnecessary since we're only running one container per host, and we already had Datadog running on the host machine. So now we want to build a container, but how do we build it? We had some issues building containers with secrets. We didn't want to have published containers with secrets in them, but builds require access to private artifacts like Ruby gems and Scala jars. And those require authenticated access to our artifact repos. So to work around this, we built a new service that could build containers and have access to secrets from within our infrastructure. It accepted GitHub webhooks and built a new container based on a configuration file in the GitHub repo, and built a container every time there was a push to master or a pull request. We soon figured out that it's actually much better to just build artifacts outside of containers and copy them in, and use your existing CI infrastructure. That way there's no need for secrets at build time. So now we just build all of our containers using our existing CI infrastructure. We're also looking at Docker multistage builds, which are currently available in Docker Edge. It's a very new feature. So they will allow us to build multiple containers from a single Docker file and copy artifacts between those containers. So we can have one container for CI that has secrets in it and another container for production that doesn't actually have any secrets in it. So now we have a container, but how do we deploy it? We could have used our existing Capistrano deploy, but the whole point of this was to get rid of Capistrano. So we decided to use Surf. We use Surf for a lot of orchestration. It's a decentralized member list and orchestration tool that's made by HashiCorp, who most of you are probably familiar with. In its most basic form, our deployment tool asks Surf for a list of hosts that match certain tags. Say you can say staging and web, and it sends you all those Surf hosts. And then you can send Surf queries out to that host, which is a small message, and it has the name and the tag of the container that you want to run. The host receives the query, and it uses an agent, a little program that we wrote that loads a configuration file from the hard disk that's dropped by our configuration management, and it runs the container. So how do we discover these services that are now running in Docker? Well, we kept it simple. We mapped to fixed ports on the host, and we used our existing console service discovery, as well as legacy chef-based service discovery, which continued to work since we're using dedicated hosts. So we had an application running in Docker in staging, and we wanted to get it running in production, but we had a major problem. It didn't actually work. Before I explain the issue that we had, I have to talk to you a bit about PagerDuty's network infrastructure, because it's kind of interesting. PagerDuty runs an Ipsec mesh network between all of our nodes within and between data centers to encrypt all of our traffic. If you want to know why we do this, there's a great book called Zero Trust Networks that's coming out from O'Reilly. It's written by a couple of former PagerDuty folks about why they designed our network this way. So the issue we were having is that if you look at this graph here, the latency is 20,000 seconds, or 20,000 milliseconds, which is actually our timeout. So nothing is getting through at all. We would send a few packets, and then it would stop, and almost all the traffic would die. Basically, a few packets would get through, and that's it. So we spent a lot of time troubleshooting this, designing experiments and testing them, and we figured out that packets close to the MTU weren't actually getting transmitted. Around the same time, we found an issue in GitHub about Docker and Ipsec, and Docker's issues with path MTU discovery. Basically, Ipsec has a 40-byte overhead on all packets, and it needs to be accounted for in the MTU you set for Docker. Otherwise, your packets won't be able to be sent. So we modified our Docker MTU, and everything magically started working again. So now we figured out our MTU issue, and the application worked well enough to promote to production. We ran Docker and non-Docker versions of the application in production for a few weeks, side by side, and then spun down the original non-Docker hosts once we figured out that everything was OK. So yay, now we have a service running in Docker in production. What are we going to do next? We've got Docker running in production. I've only talked for 8 minutes. So in our case, we decided we needed some generic infrastructure to run Docker services on, rather than writing a new Chef cookbook for each new Docker service. We wrote a configurable Chef cookbook called Generic App, which allowed us to create new infrastructure with a minimum of Chef code and using configuration tools like console template. Then we set out to convert a few more services to Docker using our new generic infrastructure. We chose a couple new targets, which were slightly more complicated applications. We had a lot less issues with these conversions, and most of the issues we did have were dealing with how generic our generic infrastructure could be and still meet our specific needs. We were also dealing with new types of applications, including Ruby apps, that had dependencies such as HAProxy and Nginx. For now, we kept those dependencies running on the host system rather than containerizing them. Running more services on generic infrastructure, we actually wanted to convert our logging to use standard out and standard error on the containers, rather than logging to disk and having to bind mount those drives into the container. To do this, we simply set up Splunk to collect the Docker container logs for any container that was running on any host. As we progressed, building more and more applications, we built out our set of base Docker images that we could use, as we needed one for each new application. A solid set of your own base Docker images makes it a lot easier to manage security risks within your Docker images and ensure that you have a standard way to set up certain types of applications within Docker. So our current process for deploying containers is this. We build and test our application on Travis. Then we build a container on Travis and publish that to our registry. Then we continuously deploy the application using GoCD, which is a self-hosted continuous integration tool. And then we deploy it from GoCD using our surf deployment tool. So the generic infrastructure and Docker are working fairly well, and we have a lot of applications running in that. But they only give us a few of the benefits of Docker. What if we also want to use less infrastructure and have even less code to deploy a service? Our ultimate goal is that you can create a new service by only creating one repository, the repository for the code for the service, and that is all you have to do aside from some configuration steps. So we're working now on migrating our workloads to a cluster scheduler, and we've chosen HashiCorp Nomad to be our cluster scheduler. If you want to know why we chose it, it's kind of a long, involved story, so you can talk to me afterwards. We've had to do a lot of work to fit Nomad within our network architecture with our Ipsec mesh network and our host-based firewalls. Basically, what we did was we wrote a Docker driver that wraps the Docker bridge driver and hooks into our network management tools to write all the information that we need into our core network management data. So converting applications to run on a scheduler is also a lot more involved than converting for Docker on a dedicated host. We have to make sure applications are logging to standard out and standard error, and that those logs are being forwarded to Splunk, and that they're able to get all their configuration from console template. On the scheduler, we also can't cheat and have dependencies running on the host machines, although we do make an exception for Datadog and Splunk collection. We have to run HAProxy and Nginx in containers alongside the application containers, which makes things more challenging. Applications have to be able to discover their sidecar containers, but luckily Nomad has some really good environment variable injection to tell you about other containers running in the same job. For logging in the scheduler, we didn't want to continue collecting Docker logs from disk, as this doesn't really scale well in a scheduled multi-container environment. We use Ubuntu 16.04 for our container hosts, so we decided to have Docker log to journald, and then Splunk follows that journald unit and splits out the information based on container and journald metadata into the different indexes in Splunk that it's supposed to be in. This means we have a bunch of pretty big gross regexes in our Splunk ingestion, but it works really well, and we get automatic logging from all our containers. So when we were implementing Nomad, we really wanted to be able to see metrics for all the containers so that we could say, hey, for this service, I want a minimum of 5 containers running, and notify me if there are less than 5 containers running. Nomad ships with a Datadog integration, but it doesn't really work in practice. It's designed for Graphite, not Datadog, so it doesn't actually use tags at all, and anyone who uses Datadog will know that tags are sort of the core of how you do anything in Datadog. So this didn't work for us, so we wrote Datadog agent checks for the Nomad server and client that use Nomad's HTTP API to collect all the information we need and report it to Datadog. With the scheduler, the deploy is going to look somewhat similar to our current container deploy with Travis and GoCD, but with a homegrown service that's running the job files on the Nomad scheduler. We store all of our job files in service repositories in a standardized location so that the deployer knows exactly where to look and what to do every time it runs. So that brings me to some of the things that I would suggest you think about when you're considering implementing Docker or another container technology in your organization. The first thing you need to ask yourself is, do I actually need Docker? What problem am I trying to solve? Are there other ways to solve it? Am I just wanting to use Docker because it's cool? Docker is great at solving certain problems, but do you have those problems? I have to admit, we didn't actually think this over super hard, so we're really lucky everything worked out very well. Because the thing is that in the end, no one really actually wants Docker or a platform as a service. They just want things to be better. They want to create services with less infrastructure code and minimal hassle. The technology doesn't actually matter. As long as it's reliable, it works, and it makes things better. You also have to think about what you actually want to use containers for, and this had better link back to the problem you're trying to solve. Containers can do a lot of things. They can do local developer environments. They can do continuous integration. Or you can use them as a way to run an application in production. These are all great uses for Docker, but they have very different benefits for your organization and obviously very different paths to achieve them. Once you decide that containers are the right approach for you, start small. Don't forget about Agile when you're working on operations or SRE projects. Keep it simple. Begin by trying to get a Docker container to run locally, even if it can't connect to supporting services. Show that it can start up and log. You don't have to worry about service discovery or configuration. Next, you can get it running in staging or another test environment where the supporting services are available. How does it find those supporting services? How do you get the configuration on the server to be in the container? Don't forget that you can use your existing tooling. You don't need to reinvent your service discovery and configuration management just for Docker. You can still use Chef or whatever for configuration on the server. And you can still use Chef searches for service discovery, if that's how you do it. Next, you have to get the story together for your other supporting services. How are you collecting logs? How are you sending metrics? These are really important and need to be standardized across all of your containers. Our first Docker app service still had its own Chef recipe, and it logged to a mounted drive that was Splunk collected, and it was very, very basic and simple. So do it simply and iterate. If you have a brand new service that you can make Docker native from the beginning, that's really great. But it also can mean that you don't learn as much doing it, and you don't have a performance baseline to compare Docker against. Once we had converted a few existing applications to Docker, we felt a lot more comfortable developing and deploying some new services into our Docker infrastructure. Many of us probably, though, have a lot of existing services that we want to make easier to deploy and manage. And Docker is great at that. But they come with their own set of challenges. When we're working with an existing application, you actually have to pick the application that you're going to Dockerize first. That can be a challenge. The best choice is usually a well-tested, stable application with known and well-instrumented performance characteristics. Something simple, preferably, that you can test easily to see if it's performing its task. Our first one was a data API, so we could say, write this to the API, retrieve it from the API, and know that it's working. Having known and well-documented performance characteristics is very important because it's helpful to see if Docker is causing any performance issues. You can fire up a metrics page with Docker on one side and non-Docker on the other side and see what's what. This was really helpful for us to demonstrate to folks like our engineers that Docker wasn't causing any major performance issues and that our Docker infrastructure actually worked. It's also important to consider the people. Who's the team that owns the service you want to convert to Docker? Do they have the resources to learn a new technology? Are they early adopters? Are they willing to take the risks? They'll continue to own the service after it's converted. So you have to ensure that they both want and are able to maintain it. So who does the actual work of Dockerizing? Is this a product-focused team doing the first Dockerizing of an application? The approach we took was that our SRE team would actually handle the first couple conversions to Docker to enhance our learning and also set some standards and improve our documentation for other teams in the future. It exposed the rough spots in our tooling and documentation so we could clean them up before other teams had to deal with them. Once our knowledge was strong and we had good documentation, we worked alongside service teams to convert the first service to Docker. After that, the teams were able to take off running on their own, and we're pushing to move more of their services to our Docker infrastructure. One constant, whether you're using Docker or not, is troubleshooting. Applications will always run into issues, regardless of whether they're running in a container. Containers just give you another thing to worry about if it's causing the problem. One thing we found, especially in the earlier days, was that it's better to have a base image that you're operationally familiar with. We use Ubuntu on our servers, so we use Ubuntu for our image base, because we know how to do things like install packages and run commands. When we're trying to troubleshoot something inside a container, it's not the time you want to be Googling how to do something. Alpine is great for small image sizes, but you have to remember how to install a package in it, and it's different from the base system that you're running on the rest of your servers. This isn't directly related to Docker, but I wanted to bring it up since it's helped us solve some of the problems we had. When you're troubleshooting an issue, it can be very helpful to be very scientific about it and always design experiments to test hypotheses and then run those experiments. This helped us solve our MTU issue in a very systematic way that felt like we were always making progress rather than just flailing at possible solutions. So at PagerDuty, we're a DevOps organization. Engineers are on call for their own services. So we wanted to convert to Docker, but we had to get their buy-in because their operational practices are going to change. One thing I've talked about already is that you have to have a concrete goal when converting to Docker. Engineers don't want to change their operations just to have the new hot thing. You have to sell it to them. We were making it easier to upgrade and manage their languages and dependencies, as well as getting rid of Capistrano. This helped immensely to get buy-in from our engineers. They didn't want to be stuck on old versions of Ruby or Scala. We also updated or helped with updating the runbooks for all the applications that were converted to Docker so that they were up to date as soon as the Docker image versions were deployed. The last thing you want to do is be in an incident with incorrect runbooks. So we've made it far easier to launch a new service with standardized infrastructure to run Docker containers. It's also much easier to adopt new languages and upgrade existing ones, which we've done much more frequently since converting to Docker. Throwing Capistrano away on many of our projects has also been a big win. Our new deployment system is much less complex thanks to deploying with Docker rather than having to manage a lot of dependencies and files throughout the deployment. With our scheduler, projects will be able to launch without any infrastructure code changes at all, with just a job file within their repository and a few setup steps. With our DevOps ethos, our engineers are also responsible for their own underlying infrastructure. With the Nomad scheduler, engineers won't have to worry about that as much anymore because it's shared infrastructure that will be managed by the SRE team. It's not all champagne and roses, though. Docker gives you a whole new layer of things to worry about. Is this network blip we're seeing because of Docker? Until you're experienced with it, it can be really easy to blame errant behavior in your applications on Docker. Troubleshooting can be a bit harder, as you have a new layer of abstraction. Visibility from the host into the container is not as good as it should be. Sometimes you have to exec into a container to get the information that you actually want. I've said this before, and I'll say it again. If you want to use Docker, don't spend a whole lot of time thinking about it and planning. Just start doing it. Build a Docker container for one of your apps. Try running it in staging. Figure out the issues as you go. You'll get it done a lot more quickly than if you sit and plan and think about it for a few months before you actually start. Thanks.
Thank you, Mia, so much for this talk. We do have some time for questions. Yes.
Just had a question about your config management for your Docker containers. Are you still bind mounting volumes for?
No. So for our scheduler containers, we can't really do that. So we use Console Template, which is another HashiCorp tool. We're sort of on board with HashiCorp, so we have Console and Vault. And Console Template is built into Nomad. So you can, in a job spec, just specify a file that it should write, and it gets all those variables from Console or from Vault for secrets.
All right, question over here.
Have you considered Kubernetes, or a distribution of Kubernetes?
Yeah, so we actually we sort of did a review of all the different container schedulers that were available. Kubernetes was definitely something we considered. Its assumptions about network infrastructure made it challenging for it to fit within our existing infrastructure with our IPsec setup and our host-based firewalls. So we didn't actually use it, but again, it's maybe something, especially given the adoption rates that it's getting, that we'll have to consider in the future.
All right, we have one here.
Yes, I'm curious if in your journey you came across components or software that you concluded doesn't actually belong in Docker.
one thing that we tried out initially was doing things like running Splunk or running Datadog in a container alongside. And we're already running Datadog and we're already running Splunk on all of our host machines anyway, regardless of whether it's running Docker containers. So stuff like that, we were just like, we can just write an IP tables rule or just write something to disk and have it picked up. So you can containerize everything if you want, but some of those more basic shared tools, sometimes it's easier to just run them on the host.
Just to follow up on that last question, did you containerize databases as well?
No.
Just making sure.
Simple answer.
About the networking stack, I assume you're not using any sort of overlay networks, or just you publishing to the ports on the host?
Yeah.